Here is a claim you can test all afternoon and never break. Take any even number, 4 or larger, and it is the sum of two primes. 10 is 3 plus 7. 28 is 5 plus 23. 100 is 3 plus 97. That is Goldbach's conjecture, written down in 1742, and after nearly 3 centuries, no one has proved it. Not because it looks hard on any single number, every case anyone has ever checked simply works, but because there are infinitely many even numbers, and checking cannot reach them all. This channel has a whole video on the conjecture itself, so we will not relitigate it here. What this video is about is how close mathematics has actually come. Not a proof of Goldbach that is still missing, but a theorem proved in 1973 by the Chinese mathematician Chen Jingrun that lands a single step away from it. It is widely regarded as the closest anyone has gotten. To see how close, we first need to look at the shape of the problem, and that shape is a scatter of dots people call the Goldbach Comet. Every even number can be split into two primes in more than one way, and it is worth counting how many. 10 splits two ways, 3 plus 7 and 5 plus 5. 28 splits two ways as well. 100 splits 6 ways, from 3 plus 97 all the way to 47 plus 53. As the even numbers grow, the number of splittings tends to grow with them. Now plot that, along the bottom, the even numbers. Up the side, how many ways each one is a sum of two primes. Every even number becomes one dot. Do this for the first 10,000 even numbers, and the dots do not scatter randomly. They stream upward in a bright, widening band. Because of its tail, this picture is called the Goldbach Comet. Two things about the comet matter. First, the band drifts steadily higher, so large even numbers have many representations, not few. Second, and this is the whole game, not a single dot ever touches the floor. Across every even number anyone has plotted, the count is at least 1. The comet never lands. Goldbach's conjecture is exactly the statement that it never will. So the evidence looks overwhelming. And it is as evidence. By the 2010s, the conjecture had been checked by computer for every even number up to 4 times 10 to the 18th. That is 4 followed by 18 zeros. Not one exception. If sheer weight of examples were a proof, Goldbach would have fallen long ago. But it is not a proof. And the reason is simple. A verified bound, however staggering, is still a finite wall, and beyond it lie infinitely many even numbers you have not touched. A single counterexample past the wall would end the conjecture, and no amount of checking below the wall can rule that out. To actually prove the comet never lands, you need an argument that speaks about all even numbers at once. That kind of argument is what number theorists have been building for 100 years, and it does not attack Goldbach head-on. It sneaks up on it by relaxing what you are allowed to call the two pieces. To do that, we need a slightly larger cast of numbers than the primes. Every whole number above 1 is built from primes, and we can grade a number by how many prime factors it uses, counted with repetition. A prime uses exactly 1. 7 is just 7. A number like 15 uses 2, 3 times 5. So does 21, 3 times 7, and so does 4, 2 times 2, and 9, 3 times 3. These two-factor numbers are called semiprimes. 8, by contrast, is 2 times 2 times 2, 3 factors, so it is neither. Now group the primes and the semiprimes together into one family, numbers with at most 2 prime factors. Mathematicians write this family as P2. A number is a P2 if it is prime, or a product of exactly 2 primes. Nothing more complicated than that. 15 qualifies, 7 qualifies, but 30, which is 2 times 3 times 5, does not. The reason this family matters is that it is only slightly bigger than the primes, and yet it is enough to loosen Goldbach into something you can actually prove. That loosening was the breakthrough of a sieve. The tool is called a sieve, and the first person to aim it at Goldbach was Brun, around 1919. This channel has a separate video on his method, so here we only need what it buys us. Brun could not produce 2 primes. What he could produce was a weaker sentence. Every large enough even number is a sum of 2 numbers, each of which has only a few prime factors. His first version allowed each piece up to 9 prime factors. This gave the field a scoreboard, and its notation is the key to everything that follows. Write a plus b to mean every large even number is a sum of a number with at most a prime factors and a number with at most b prime factors. Brun's result was 9 plus 9, and in this same shorthand, Goldbach's conjecture, prime plus prime, 1 factor and 1 factor, is simply 1 plus 1. So the whole quest now has coordinates. Everyone is trying to drive both numbers down, a and b, as low as they will go, and the target sits at 1 plus 1. Brun opened at 9 plus 9. What happened next was a 50-year descent. Think of the results as a ladder, each rung a smaller pair of numbers than the one above, all of them reaching down toward 1 plus 1. Brun's 9 plus 9 in 1919 sits at the top. Rademacher brought it to 7 plus 7, Esterman to 6 plus 6. Buchstab stepped it to 5 plus 5, then 4 plus 4. Wang Yuan reached 3 plus 4 in the 1950s. Every rung was a genuinely hard theorem, and every rung shrank the two pieces a little further. Then came a different kind of progress, getting one of the two pieces all the way down to a genuine prime. Pan Chengdong reached 1 plus 5, a real prime plus a number with at most 5 factors, then 1 plus 4. Then, in 1965, several people independently reached 1 plus 3. The lower number was stuck at 1, a true prime. The fight was now entirely over the other piece, 1 plus 3, a prime plus a number with at most 3 prime factors. The goal, 1 plus 1, was now just too short, and there the ladder seemed to stop, until Chen Jingrun found the next rung, and it was the last one anyone has managed to reach. Chen Jingrun's theorem, announced in 1966 and proved in full in 1973, is the rung 1 plus 2. Stated in words, every sufficiently large even number is a prime plus a p2. That is, a prime plus a number that is itself either prime or a product of just 2 primes. One genuine prime, and one piece that is at worst a semiprime. It is the closest anyone has legally come to prime plus prime. Look at how thin the remaining gap is. Goldbach wants the second piece to have 1 prime factor. Chen guarantees it has at most 2. The entire unsolved distance between the best theorem and the famous conjecture is the difference between a number that might be a single prime and a number that might, at worst, be 2 primes multiplied together. 1 rung. And that 1 rung, as we will see, is not a matter of trying harder. Let us make Chen's guarantee concrete on a number we already met, 100. Goldbach says 100 is a prime plus a prime, and indeed it is, 3 plus 97, both prime. That is the 1 plus 1 we cannot prove in general, even though we can obviously see it here. Chen's theorem promises something weaker but provable for all large evens, a prime plus a number with at most 2 prime factors. For 100, take 5, which is prime, and 95. 95 is not prime. It is 5 times 19, a product of 2 primes, a semiprime. So 100 is 5 plus 5 times 19, a prime plus a p2, exactly the form Chen guarantees. The difference is right there on the screen. In the Goldbach line, the second piece, 97, is 1 clean prime. In the Chen line, the second piece, 95, splits into 2. For 100, we happen to have both. Chen's achievement is that the second kind of statement can be proved to hold for every large even number, while the first kind cannot. There is a caveat in Chen's theorem worth stating honestly, because it is easy to gloss over. The guarantee is for every sufficiently large even number. That phrase is doing real work. The proof shows there is some threshold beyond which every even number is a prime plus a p2. But the original argument does not hand you a small, explicit value for that threshold. It proves the wall exists without cheaply telling you where it is. The small even numbers below it are not covered by the theorem itself. They are checked by other means. This is a normal situation in this part of number theory, and it is why Chen's theorem, for all its power, does not settle any one particular even number for you. It is a statement about the far tail of the number line. That honesty matters, because it separates what is proved, the eventual rule, from what is merely checked, which is the near end. And it sets up the real question. If we have come this close, one rung away, why can we not simply take the last step to 1 plus 1? The last step is blocked, and not by a lack of effort. There is a structural reason identified by Atlee-Selberg, called the parity problem. Here is the heart of it. Every sieve at bottom sorts numbers by counting their prime factors. But it turns out a sieve can only ever see that counts parity, whether the number of prime factors is even or odd. It cannot pin down the exact count. Now watch what that does. A prime has exactly one prime factor, an odd count, but so does 8, which is 2 times 2 times 2, 3 factors, and 30, which is 2 times 3 times 5, also 3. To a sieve, 7 and 8 and 30 look the same on the one thing it can measure. All 3 are odd. So a sieve cannot separate the genuine primes from the numbers with 3 or 5 or 7 factors. It cannot isolate exactly one. Goldbach needs precisely that separation. The second piece must have one prime factor, not 3, not 5. Chen's theorem squeezed the sieve as hard as the parity barrier allows, down to at most 2 factors, which is 1 even and 1 odd count mixed together. Pushing to exactly 1 crosses the wall Selberg identified, until someone finds a genuinely new tool. That is why 1 plus 2 is where the ladder ends. Chen proved a second theorem the very same way, and it lands just as close to a second famous conjecture. The twin prime conjecture says there are infinitely many primes that come in pairs 2 apart, like 3 and 5, or 11 and 13, or 17 and 19. Like Goldbach, it is open. Chen's cousin result relaxes it in exactly the same style. He proved there are infinitely many primes such that the number 2 larger is a P2 prime, or a product of 2 primes. So take a prime, add 2, and you are guaranteed, infinitely often, a number with at most 2 prime factors. 7 is prime, and 7 plus 2 is 9, which is 3 times 3, a semiprime. 19 plus 2 is 21, 3 times 7. The pattern never runs out. Same shape, same barrier. To upgrade this to the full twin prime conjecture, you would need that P2 to be an actual prime, 1 factor, not 2, and the same parity problem stands in the way. 2 of the most wanted conjectures in mathematics, and Chen brought both to within a single, well-understood step. Step back and look at the whole distance traveled. A century ago, the best anyone could say was that a large even number is a sum of 2 numbers with at most 9 prime factors each. Today, thanks to Chen, we know it is a prime plus a number with at most 2. 9 and 9 became 1 and 2. The comet has been climbed almost to its floor, and the floor has never been touched. Every even number ever tested is still a sum of 2 primes, and no proof yet reaches all of them. And the gap that remains is precise. It is not vague or vast. It is the difference between a number with 1 prime factor and a number with 2. And it is guarded by a barrier, the parity problem, that we understand well enough to know that current sieves cannot cross it. Chen Jingrun did not solve Goldbach. He did something that in its own way is just as clarifying. He pushed the old method to its exact limit, and showed us, to the factor, precisely how far it can go, and where the real wall begins.